Good afternoon, everyone. My name is Joon-Hyuk Park, and I'm an assistant professor in Mechanical Aerospace and Engineering Department, and also a member of Disability, Aging, and Technology Cluster. My lab is Wearable Engineering and Assistive Robotics Lab, Wearable, and I'm happy to share my research about wearable assistive and rehabilitation technologies for disabled and aging population. So just brief introduction of myself here. The basis of my research is mechatronics and robotics, particularly their applications to wearable devices and robots, focusing on assistive and rehabilitative technologies. Since the research is related to understanding how human moves, interacts, and adapts to external devices and robots, there are other areas outside engineering that I work on, such as movement biomechanics, kinesiology, and physiology. And all my research heavily involved experimental studies for device method validation on human subjects. I teach undergraduate and graduate level mechatronic classes where students learn the fundamentals of mechatronics, such as mechanisms, power transmissions, actuators, sensors, microcontrollers, circuit design, logics, and algorithms, with hands-on experience through 8 lab sessions and a final project. So today, I'll be sharing 3 topics. 1, variable resistance suit. 2nd, work sharing of upper and lower limbs. And the 3rd, patient transfer robot. Just a quick overview of my research objective, which is research and development of new methods and tools to enhance the practicality, utility, and intelligence of wearable and assistive devices in application to disabled and aging populations. And I use multidisciplinary approach to address complex problems. There are 3 areas: design and control, sensing and learning, and human-over interactions. So this research project, Variable Resistance Suit, is a resistance training device for sarcopenia, prevention, and intervention. I'm collaborating with many faculty within UCF across kinesiology, physical therapy, nursing, statistics, and NIH R3 is currently under review. The objective is to test the validity of variable resistance suit as an effective, safe, and home-based resistance training device for sarcopenia prevention and intervention. So the most common resistance training method for older adults to treat sarcopenia is utilizing resistance band, which we identified several gaps and limitations. 1, the level of resistance force is not measurable or tunable. 2nd, unidirectional and position-dependent resistance based on the amount of stretch of the material, which can exert undesirable strain to body joints or muscles. And as you can see, this method affects entire limb across multiple joints, which is not appropriate for use by individuals with pre-existing musculoskeletal injuries or conditions. And lastly, potential risk of balance loss from restorative forces when poorly instrumented. So based on these identified gaps, we designed this device called VARS, Variable Resistance Suit, which offers quantifiable, tunable, and bidirectional and speed-dependent resistance that can be targeted to a specific joint and muscle group. It consists of 3 rotary dampers interconnected using belt and pulleys, from which it gives us 8 different resistance configurations. So this study includes 3 different assessments. 1 is functionality assessment, 2nd is training outcome assessment, and the 3rd is usability assessment. In functionality assessment, we validate speed-dependent bidirectional and adjustable resistance modulated by VARS with 3 different speeds under each 8 different resistance levels are tested. And then we measure muscle activation using electromyography to compare how muscle force changes in response to these conditions. Then there is a 8-week-long resistance training using VARS to assess muscle hypertrophy induced by VARS. We compare baseline, which is pre-training session, and mid-training session at week 4, and the post-training session after completion of 8-week-long training. The study participants come to the lab 3 days a week and exercise upper arm and thigh muscles using VARS. And upon completion of training sessions and assessment, participants provide their feedback on device usability in terms of form, heat, and comfort. Our preliminary results of VARS device functionality assessment showed that the muscle efforts or force increases with increasing resistance across 8 different levels as expected, which validates that the device does provide adjustable and quantifiable resistance force exerted on the human body joints. We have conducted training outcome assessments on 12 subjects, and the results showed significant increase in muscle strength between baseline and then the post-training, and also the mid-training to the post-training. So the overall increase in the muscle strength is about 30%. And also ultrasound imaging to measure the muscle cross-sectional area and thickness also showed similar results, indicating 16% increase in muscle cross-sectional area. So the impacted outcome, these FARs can provide new resistance training tool and technique that may enhance the effectiveness and safety of current resistance training modalities for older adults, thereby improving sarcopenia prevention and intervention. Next study, we will assess the efficacy of FARs-based resistance training compared to other methods, such as weightlifting and resistance band-based methods. And we'll preparing NIH R1 proposal to include older adults with and without sarcopenia, where they will use FARs for at-home resistance training over 8-year-long period. The next research topic is called WOOL, work sharing of upper and lower limbs. So when we walk, we swing our arms primarily to help maintain gait and postural stability, where upper limb muscles are minimally utilized. Prolonged walking increases metabolic cost and lower limb fatigue, while upper limbs are not as fatigued as lower limbs. So the idea is to harness the kinetic energy of the upper limbs during walking and transfer it directly to the lower limbs via external mechanical connections, help reduce the efforts of the lower limb during ambulatory movements. So this is the WOOL model, where we use wearable interfaces and cables that connect upper limb joints to the lower limb joints. The anticipated effect of WOOL is that we increase the upper limb muscle efforts by sharing the work of the lower limb, and in return, the lower limb muscle effort is decreased. There are 3 aims of this research. One is to identify optimal mechanical connection between upper and lower limbs. Second is to find optimal work sharing ratio and joint pairing. And the third is experimental validation of different WOOL strategies. We've conducted a preliminary evaluation of a WOOL prototype during single leg flexion, extension, and then a sit to stand, as well as step up and down motions. So the results show that WOOL reduce knee flexor and extensor activity during these ambulatory movements up to 20%. And then the next steps are finding optimal joint pairing between upper and lower limbs. So shoulders and elbow, which joints should those be connected on at the lower limbs, and using what work sharing ratio, such as 50-50, 30-70, or 20-80%, that would yield most energetically efficient and safe work sharing between upper and lower body. So we have these 3-tier gear system that will allow us to explore that different work sharing ratio between upper and lower limbs. And then we have experimental protocol that we will conduct to address that question. This idea can be extended to human physical augmentation, where soldiers can use upper limb motions and forces to boost speed of running or jumping. And I'm in contact with several DoD agencies to seek for funding. I have 2 other research that I want to quickly share. One is patient transfer robot, which is in collaboration with rehab clinics at Orlando Health and Advent Health. The goal is to develop and test an autonomous patient transfer robot that integrates multiple modules to effectively and safely perform patient transfers without the need for caregivers' assistance in both healthcare facilities and home environment. Another research is multimodal human and ambient sensing, where we built the custom PCBs that integrates various human physiological and ambient sensors with onboard data processing analysis capabilities. And the goal is to implement onboard real-time machine learning-based classification model to inform different states of human physiologic parameters with real-time data sharing so that doctors, caregivers, and next-up team can monitor the status. So these are the short and long-term goals or plans. So for the grant proposal, I'm currently preparing an answer prayer to be submitted this summer. And there are a few R1 and R3 grants that are already submitted and also in development. And the second short-term plan is to strengthen multidisciplinary and multi-institutional collaborations within UCF and outside UCF, since I already made connections to the local medical centers, Orlando VA, Orlando Health, and Advent Health. And as a disability aging and technology cluster member, I would like to contribute to the center grant. In terms of education, refine and improve lecture materials and labs for the mechatronic classes that I'm teaching. And then I'll have my first 2 PhD students graduating to be expected in fall 2024. Long-term plans, sustainable lab with several research lines supported by main federal grants, accomplishments in the field of wearable device and robot design and controls, and technology transfer of research prototypes. In terms of education, I plan to develop course materials to offer analysis and control of robot manipulators, which has not been taught for years. So that concludes my presentation. Thank you for listening, and I'll take any questions or comments. Thank you.